This should click. There we go. All right, so I'm going to start with a little bit of history about WebAssembly. It's funny in that the execution tiers of WebAssembly have basically arrived completely backwards, starting with the optimizing JIT compiler. Almost universally, when you build a VM, you start with an interpreter. We did it totally opposite. And the reason why is that the assumption was that the top tier code quality was the most important thing. It was justified to do upfront compilation. I'm pretty sure I uttered these exact words in some back room when we were designing WebAssembly. Interpreter performance doesn't matter here. We're not designing for that. And of course, history made me eat my words, and here I am to basically grovel before you that that was wrong. We did design it, WebAssembly, as a to give it the ability to do fast single pass validation. So we didn't completely screw that up. It wasn't like everything went out the window for optimizing compilers. Yet, when it did ship in 2017, every engine was using pretty much only their optimizing compiler to execute WebAssembly. So in Chrome, that was Turbofan. In Firefox, that was OdinMonkey. GSC, they used their top tier JIT, and also in Chakra. Chakra was the only one to have an interpreter for WebAssembly. And I thought that they were insane and that that was a joke, but actually it turns out to be maybe forward thinking. In reality, when you only use the optimizing compiler, you have a major startup pause, even if you throw many compiler threads at it. So, again, going with the theme of doing things completely backward, then you start with the next tier down, which is a baseline compiler. This was part of the plan, single pass validation, also single pass compilation. And the idea is that you do not build an intermediate representation of the code, you just do one pass, single pass forward register allocation, and it is totally worth it. You can get a 50x improvement in compilation speed. The code that you get out is not quite as good, so it's going to run, it's going to be both larger and run slower. In reality, this is such a big win that all the engines are doing this now. So they all have at least 2 compiler tiers for WebAssembly. And yet, programs are still getting bigger, so that space is an issue. There are modules out there that are over 200 megabytes. These are whole applications, and so memory consumption is still a huge issue. Which motivates finally finishing the last tier that's missing, an interpreter. So I wrote an interpreter in V8 that was designed just to be for debugging. That was in C++. It was like 1,000 times slower than the optimizing compiler. It turned out that that's not what's used in V8 to debug WebAssembly code today. But there are other reasons that you might want to use an interpreter for WebAssembly or any other format. Cold code, meaning code that's executed once or maybe not at all. Startup time, you don't want to do any processing for code that's not going to run very often, and you don't want to spend any space on it. Interpreters are great if you want to instrument, trace, step through the code, debug it. This is like the thing that you want. You don't want to debug the optimized code or step through it. And generally speaking, bringing people to WebAssembly, bringing new languages to WebAssembly, it helps if they have those abilities because it's just so much easier to debug your broken code that you got from your compiler if you have an interpreter. You can trust an interpreter more, so you can prove the correctness of an interpreter. And also, if you're experimenting and adding new things to the format, then it's easier to do in an interpreter. But WebAssembly is not easy to interpret. In particular, a primary thing is that control flow constructs are all structured. You have blocks, you have loops, you have ifs, you don't have jumps. So if you have control flow in your code, the interpreter would not know where to go. So the destination of branch isn't known. Also, exception handling will be a part of WebAssembly, and those have additional bytecodes where you also don't know where to go. There are interpreters for WebAssembly now. So JavaScript Core in particular has grown an interpreter for WebAssembly. Chakra originally from the beginning did have one, but there's also some other embedded systems that use WebAssembly interpreters, and they all rewrite the bytecode. So they all have chosen an internal format, which is easier for an interpreter to deal with. And of course, the downside is that you have a copy of the code. So it's at least double the memory consumption. It takes time to generate that format. And actually it's complex too. So it's on the order of writing a single pass compiler. So all these approaches have complexity and space overhead, and that's why we want to do it today in place. And that's what this paper is about. So we take the original bytes unmodified off the network in the module, and we are going to interpret them in the standard style. And the trick here is that we need to have some additional information called the side table. So the side table is going to be pretty small. It's going to save a complete rewrite step, both the time and space associated with that. This is not the first time that I've used a side table. So the one that I wrote in V8 originally, there was a side table, but it required search. So every control flow operation was a login operation. So the trick here is that now it's O1. There's also another engine that does use a dynamic control cache, but they don't. They have some pathologies that you can see in the paper. I'm not going to talk about that because I don't have time. It's pretty fast. So basically reaching parity with JavaScript Core's rewriting interpreter, and it has much better space utilization. How does it work? So if we imagine this green box over here, this pale green color here, on the left, that's the code. That's the WebAssembly code shown disassembled, but obviously it's just the bytes. And there's various state things here in an interpreter. So obviously you need to keep a pointer into the code, a pointer to the end of the code, because you're legally allowed to fall off the end. That's returning in WebAssembly. You have a value stack. That's the actual data values of the executing program, so a stack pointer and a frame pointer, the locals, and the operand stack. There's this sort of global context too, but the new thing here, which is really in concert with the code itself, is this side table. And so there's a pointer into the side table that contains the information that you need to do the control flow, which is not in the bytecode. So this side table is organized and sorted. So if you look at the code on the left, there's these little blue circles. Those are the control flow instructions that need a little bit of help to execute them in an interpreter. So each one of those has an entry in the side table, and the entries in the side table tell the interpreter how far to move the instruction pointer, if we are going to take that branch, how far to move the side table pointer, and also what to do with the operand stack. And the key thing is that how to move the side table pointer gives this O1 overhead. So we never search the side table, it always points at exactly the next entry. So when we take a branch, we also adjust it. That's the key idea behind the side table. All right, so now let's implement it and let's run it. So we have to make some design decisions. I've been working on a new WebAssembly engine for research called Wizard, so I figured that this would be a good vehicle to try out whether it's flexible and interesting. I implemented it in Virgil, which is a language I've been working on for many years. Then you have to make many other decisions about how the interpreter works, how values are represented, how does the dispatch mechanism work, how does the execution stack work. These are the choices I initially made. And an algebraic data type in Virgil, these are very much like an algebraic data type in Haskell or ML. These are immutable values. They have a tag. They're like a discriminated union. It makes really nice, clean, easy to read code, so you can write a nice looking interpreter. They have the right semantics because they're values and they don't have identity. But the default implementation in Virgil is to box them on the heap. And interpreters like traffic in values left and right. It's one of the hottest things in the whole interpreter. And this is what happens. So this is execution time. Higher is worse. The baseline 1 would be JavaScript Core's interpreter. And so this is like absolutely horrible. This is like 100 times slower than JavaScript Core's interpreter. And even in the best cases, it's like 20 times slower. So if you're a grad student and you implement an interpreter and you're 20 times slower than the state of the art, you got to just rewrite an assembly, which is what I did. So I spent almost a page justifying why I wrote all of this in handwritten assembly code. And the reason is that you can't get the signal that you want writing in a higher level language that's got a lot of dynamic checks or maybe an inefficient representation. So we changed the design choices a little bit. Same engine, we're going to use assembly language now to implement the core of the interpreter. Change the value representation so that things aren't boxed on the heap. Obviously, the allocating an object for every instruction executed was not going to be particularly smart. The dispatch mechanism, so basically the thing that runs the loop, we can do some tricks there, and I'll mention those. So all these other design decisions can be lined up behind the idea that now, if I write assembly code, I can do it however I want. Okay, first problem, solve the value representation. WebAssembly has effectively 6 different value shapes. They need to go somewhere in memory when you represent the value stack. I decided to use a value tag, which means that each value is distinguished by having an actual tag on it in memory. And there's a couple of reasons for that. One, the garbage collector needs to know what's a reference and what's not a reference, so to be able to distinguish the bits of an integer from a reference. The other thing is that it's designed for programs to actually instrument WebAssembly and run. So they're going to actually look at the value stack. So you want to kind of know what when you present a view of the program executing, you want to show them what the types are. And they might modify them too, so there's some checking. So the value representation here is actually really fat values. It's 32 bytes, so every slot is 32 bytes. And the reason why is that there's at least one really big value in WebAssembly, which is a 128-bit vector, which is 16 bytes. So if you add 1 byte for a value tag, you're now at 17, rounded up to a power of 2. That's how you get 32. So the value stack is separated from the execution stack here, and there's reasons for that. I won't go super detailed into that. But the rest of the design decisions line up here. So we're writing an assembly, so we can put all the state of the interpreter in the architectural registers. So that's like mostly just a mapping. I did do some careful tuning so that the important ones go in the right registers. That saves me a byte in the encoding and things like that. But pretty much, you can execute the entire interpreter without doing any spills. So it's all just running with the architectural registers. You don't need to do bounce checks on the code because verifying WebAssembly code means that the program can't jump outside of the code. Same for the side table. So this invariant is something that you cannot really express in a general purpose language. So you basically just have to not do those checks. I mentioned unboxed values, but also checking for stack overflow. So if a program is executing unbounded recursion using too many values, you want to actually terminate the program and give them a nice stack trace. So instead of doing a branch, an actual check for every stack operation, there's a guard page. Same for the execution stack. They grow in different directions. Another thing about the WebAssembly format, it just so happens that the way local variables are numbered and the way the operand stack works, you can actually overlap the frames so that there's no copying arguments on calls. You can only do this if you separate these two. Okay, there's some fine tuning here in writing the assembly code, which I really enjoyed, but also was a bit of a chore debugging that. So when you execute a WebAssembly function, you actually have to decode the declarations of locals. So I wrote the tightest possible assembly code that I could get to make that fast. It turns out that the dispatch table, which is the thing that holds the addresses of where to go for each bytecode, making that smaller saves data cache space. So making that 4 bytes and putting all of the code of the interpreter in the low 4 gigabytes of address space, that was like 5%. That was a 5% performance improvement to go from 8-byte entries to 4-byte entries. There was even bigger performance to be had by dealing with these variable length integers that show up a lot in the format. They're called LEBs, so I hand-rolled all of that. And then a big win is this thing called threaded dispatch, which has been known for multiple years, for many decades, which is you have the dispatch sequence copied at the end of every opcode handler. This is worth up to 40% execution time in the interpreter. So that's the big one, and that's really hard to do in a high-level language. All right, so if you do that, then this is the same benchmarks, this is the same graph, same baseline, so it's not 100 times slower. Now we're within 40% on the top end, and maybe can be 20 or 30% faster. So it's like some plus, some minus. There's several versions here. You can see the difference between the blue bar and the green bar is what all the assembly tuning that I did, how much does that benefit? And can be 20 to 30%. The value tags, I was also curious, how much do the value tags cost? Because those have to be dynamically tracked by the interpreter, and it's not as much as I thought. It's only about 8 to 10% of execution time for the value tags. So I think that was worthwhile because it made the interpreter a lot more robust. All right, so this is a bigger picture. So this is putting WebAssembly interpreter in the context of the other execution tiers that I mentioned. So the green bar here is actually not going to be Wizard's interpreter. It's actually going to be the fastest interpreter for WebAssembly that I did find that does rewriting. That was Wasm 3. So that's an interpreter. That's the green bars. You can see them trending, getting bigger. The benchmarks are the same as before, but they're sorted by their execution time. So on the left-hand side, these are the shortest running benchmarks. They're maybe 100 milliseconds each. And then trending towards the right is more like 2 seconds. And that's key because you see something very interesting here. So we've got optimizing compilers in the mix, we got baseline compilers in the mix, and then an interpreter. So the red bars are the optimizing compilers, the baseline is an optimizing compiler, and then the blue bars are the baseline compilers. Interpreter wins if your program doesn't run very long. We kind of knew that, but there are actual benchmarks out there. And so that's a cautionary thing if you actually have a benchmark suite that's not broad enough. You may not even see the advantage of having an interpreter, which is that for all of the cold code, it's way better because you don't spend any time compiling it, right? Also notice these four on the left here. The baseline compilers are also better than the optimizing compilers. Because right here, for the short-running programs, all that matters is how much time do you spend up front dealing with the code. In the middle of this graph, it's a bit more mixed. So there's a couple where the baseline compiler is actually best, but the interpreter is obviously not good enough. And if you had benchmarks that ran approximately in the middle, you might be tempted to conclude that maybe we should only have a baseline compiler and that like the optimizing compiler doesn't pay off. But obviously, we know that if you move to the right, you have longer programs, then eventually the optimizing compilers are going to win out in the end. Another interesting thing here is that like we can see the trend with the interpreter. Obviously, the interpreter is falling behind because these are really long running programs. It kind of levels off at about 10x. And that's like a rule of thumb that I've kind of used throughout the years. An interpreter is about 10 times slower than a compiler. And so that actually pretty much lines up with the data. That's good. Okay, so this is the same benchmarks, but this is now the interpreters only. So the baseline has changed. The baseline is now Wasm 3, which was the really fast interpreter, the fastest one. And so this is the four other interpreters that I measured. So now the green bar here is Wizard, which is my implementation. Sorry for the colors. It's because there's a global color scheme, so it's not super nice to look at. JSC is the kind of yellow bar, and then WAMR is the WebAssembly micro runtime. That's the kind of orange and brown bars. And the interesting thing here is that, yes, the rewriting interpreters, of which WAMR fast and the baseline, those are much better than doing it in place because they use representations that's hyper-tuned for interpreter performance. They use a threaded code representation, and they can be up to 2x faster than the in-place interpreter. But the the JSC interpreter, which is the one that's production in JavaScript core, it's very comparable to Wizard, and that does actually rewriting too. But actually, this is a multi-dimensional trade-off. And so this is actually the money shot here. So on the x-axis, so we've got, on the y-axis, we've got execution time. The baseline is the fastest tier of any of them. That's the optimizing compiler from V8 Turbofan. And then the horizontal axis is actually the upfront processing time for translation, whether that's translation to machine code or to an internal representation for another interpreter. And it's actually logarithmic, if you notice, right? So there's 4 orders of magnitude here. The optimizing compilers, they spend the most time, but they get the best performance out. And so they just line up in this nice little red circle. The baseline compilers, so you can see, they're much faster. They can compile almost 100 times faster than optimizing compilers, but they start to float up. You can see the trade-off that they're trading compilation time for the runtime performance. But interestingly, the rewriting interpreters actually overlap. The amount of processing time that they do can be comparable to what baseline compilers do. But since they ultimately interpret the thing that comes out of that rewriting, they're going to be much slower. So they're going to be 20 to 30 times slower. And the key thing is that now we're in a new region. So my work is in a new region where it doesn't have to do as much processing up front. The analysis that generates the side table, that happens during code validation. That's the delta. So we're able to do much better in terms of startup in this trade-off. There's actually 3 dimensions. So the other dimension is space. How much space comes out of the thing that the pre-processing, right? Whether that's machine code, whether that's another form that you interpret, and that's this graph here. Same y-axis, so it's the same in terms of execution time, but now the horizontal axis is going to be the overhead in terms of how many bytes come out per input byte. So 1.0 would be 1 output byte for 1 input byte. And so you see that JavaScript core, which is this orange one here, that lines up at about 1. That's because their interpreter representation actually is still a stack machine. These other 2, all the rest, everything to the right, is all the compilers and interpreters like kind of get mixed up. There really isn't an advantage other than keeping the stack machine. There isn't an advantage to rewriting to an interpreter form that uses, for example, registers. So like it can take as much space as the machine code. And then of course my work here is on the left. That's the side table. It takes about 30%. So for every input byte, there's about 0.3 output bytes. So you save a lot of memory. That's the point of this. Okay, so we got an interpreter. What do you use it for? Running slow, right? No, actually you want to use it for an actual purpose. One of the things is instrumentation. So there's a trick here that I use. If we're interested in instrumenting a particular point in the program, the interpreter can do this easily by just making a copy of the code and then overriding the byte of that instruction with something illegal. So this purposefully chosen ugly purple color is an illegal instruction that will cause the interpreter to hit a new handler, and that handler will call user callback. So running the original code doesn't have to do any checks for any instrumentation. You do this by making a copy of the code and causing an illegal, effectively an illegal instruction exception, and then doing the user callback. Since we've got a copy of the original code and we stopped at the exact offset, we don't have to do any translation in terms of where we were in the original code. We know exactly where we were. And we have the original code so we can execute the bytecode after we've done the instrumentation. There's another trick in the paper which I don't think has been done before in interpreters, and it's kind of a sleeper deep in there, but I think this is a really neat trick. And I'm surprised that this works. So there's other cases where you maybe want to get a callback every time the interpreter runs any bytecode whatsoever. So in this case, what I do is I use a dispatch register. So normally the dispatch register points to a dispatch table, and you always go directly to the opcode handler. But if you want to now get a callback for every bytecode executed, we just switch the register to a version of the table that points to a handler that always calls the user callback. And so by only switching one register, we now have forced the interpreter to basically go into this debugging mode. So there's no check involved. I thought it would be slower to use a dispatch table register because normally the dispatch table is like at a known address in memory, but it turns out actually to be faster. So my interpreter actually got faster by adding this ability. And this also means that we can turn it on dynamically. So we can add a probe, for example, locally to an instruction that in its callback turns on global instrumentation or vice versa and also turns it off. So you can just go back immediately. So this is like useful for things like debuggers where you have like step over an instruction. Okay, so the takeaways here is that we have a constant time side table. Everything that's done at runtime using the side table, there's directly a pointer to it. There's no searching involved. This gives us an in-place interpreter design that's performance is on par with a production rewriting interpreter. Not all rewriting interpreters, but at least one, so that's good enough. It definitely has lower memory overhead than rewriting by any measure. The other thing that I learned, and should be a lesson again that I relearn every few years, is that something about interpreters is very weird. The implementation language matters a lot. Like all the overheads that come with having a nice language, those are magnified greatly. So obviously allocating an object on the heap for every instruction doesn't fly. But there's a lot of other things that you have to do to make an interpreter fast, like you have to make sure that all the stuff is inlined. That's really hard to do in any language. C compilers still have trouble with this. This assembly actually can work here. All the machine code tricks that I could think of, those are necessary to get me from being, say, 50% slower than JavaScript core to being the same speed. So this is really one of the few places that's left where an assembly programmer by hand can beat a compiler. And those fine-tuning is really the thing that closed the gap here. Okay, future work. So I spent several months working on the assembly. There's some opportunities that are left on the table that I could see. It's not a huge thing. I don't think that I could get more than about 5 to 15%. So I'm probably not going to do that. So my time is limited on this earth, and also that's not where I'm going to focus my effort because maybe there's new things in WebAssembly that we can add. So I'm focusing my effort on doing extensions like the garbage collection proposal. I implemented that in the nice version of the interpreter, which is all in Virtual source code, but I didn't implement that yet in assembly, and I will. I mentioned SIMD instructions, so the interpreter has the value representation, all that, and all the verification around SIMD, but I didn't implement those in the interpreter yet, and so that needs to be done. And there are other things like exception handling and 64-bit memories and multi-memories. But actually, I want to make Wizard more useful to the community to actually do dynamic analysis. So that means not only the instrumentation that I have now for code probes, but also for memory and for other types of events that happen during execution. And well, actually, a baseline JIT is really important. I've already started working on one that's maybe 50 to 60% complete and see some pretty big gains, as you would expect. So that's where I'm focusing my effort. And I think that's my last slide, so I'll take questions.
Don't know if you can comment on this, but so your Wasm is done in ASM,
Yeah.
Which isn't going to work for me. But the JSE core, that's written in C++, isn't it? So
it is written in a macro assembler, so they kind of have like a weird DSL that they generate assembly code from.
okay. Right,
And the key thing is that to get that dispatch loop just right, they couldn't quite do that in C++.
Okay. Any chance of an M2?
Say again?
Any chance of an M2 version?
Yes. Do you have a graduate student?
Yeah, I was going to say, excellent graduate project.
So if your goal is to optimize like cold start performance using an interpreter, have you considered like maybe not doing verification and doing that at runtime instead? Like, because that's an extra pass over the code, right?
Like doing lazy, yeah. There's a trade-off in doing it lazily. Technically, the Wasm spec allows you to do lazy validation. I think that JavaScript core might be doing lazy validation. Chakra core actually pushed for that to be in the standard. I showed the numbers for what the overhead is, but I didn't show how much of that is, like, what is the verification cost. Verification is about 2 to 3 times of what the side table generation was. I can see a little bit of benefit, but it's not huge. So I think I'll probably keep eager validation in Wizard.
So you showed the space overhead graph, but you didn't show overhead of the runtime itself. For example, memory overhead for this dispatch table. Is that significant compared to the other?
It's in the paper. There's 14 kilobytes of machine code. There's 7 kilobytes of dispatch tables.
Okay, that's good. And another question, how come it was faster with the dispatch register? Is there some kind of prefetch happening, or?
I think those constants, so like if the dispatch table is at a particular address, that's an immediate in the code, it actually makes the code bigger.
So I was surprised that you said the construction of the side table wasn't counted in the processing because it happens during validation. So couldn't you do the same for a bytecode interpreter? Do the translation to bytecode as part of validation?
Yeah, I mean, those are significantly more expensive than the validation itself. I mean, all the numbers that I showed here are like things that I measured from the actual VMs that you do pay for and you see it at runtime.
All right, one last question from the audience so that we can switch over. Then I will take that one question. Which of these tricks can we teach our compilers? Because I don't want to write my interpreters in assembly.
So yeah, C does have an extension to do the labels as values to get the threaded dispatch. That's the biggest one. There's some work on making it easier to write interpreters in a tail call style. So you can basically just write every bytecode handler as a function, and then you do a tail call. And the key thing there is that you need to have enough registers in your calling convention so you don't spill anything. So that's promising, I think.
All right. Let's thank Ben one more time.